Hello, everyone. Good morning, good afternoon, good evening, depends on where you are. My name is Lingfei Wu. I'm currently a principal scientist in JD.com Silicon Valley Research Center. Today, I'm very delighted to talk about deep learning on graph for large language processing in the SIGIR2021. This is joined with Yu Chen from Facebook AI, Henji from the UIUC and Amazon, and Bao Liu from the University of Montreal and Miller. So first, let's take a look at outline our DLG4NLP tutorial. So there's three key components. The first we will introduce our DLG4NLP, the basic stuff. For example, why the graph very important for the NLP community, and what's the conventional machine learning methods that have been using for NLP in the last 2 decades. With the rising of the deep learning, so what's the current modern technique? For example, deep learning on graph, foundations and the various models that we have been using so far. And then we will move to the foundations of DLG4NLP. We will first talk about giving a text sequence. How can we construct a graph for various NLP tasks? We'll talk about 2 different graph construction, static graph construction and dynamic graph construction. So once we have a graph at hand, so what kind of graph representation learning technique we should choose for the current NLP task? That is really depends on the graph at hand. For example, its graph is a homogeneous graph, or its graph is multi-dimensional graph, or it's a heterogeneous graph. Depends on the different graph type, we will choose a different graph learning technique. So we will also pay special attention on a very popular variant of a model called Encoder-Decoder model. And here we will introduce a different kind of a graph-based encoder-decoder model for NLP, such as a graph-to-sequence model, graph-to-tree model, and a graph-graph model. And finally, we will select 5 representative sub-area of NLP, including information extraction, semantic parser, machine reading comprehension, natural language generation, and machine translation. And we will illustrate that how in the different application domain, people how to leverage the various graph neural nets for the NLP task. Beyond these 3 key components, we will also have DLG4NLP demo session, where we present a first library called the Graph for NLP library for the easy use of the graph neural nets for NLP community. And we will talk about the overall architecture of our library, and also we will give 2 demo case for people to study, how to cover a quick start of using our library. And finally, we will discuss the future direction of this rising, fast growing area, and we will conclude this tutorial. Okay, first part is graph for NLP introduction. So we have been talking graph a lot. So why we choose graph? So that's because that graph is really a generic language for describing and modeling a complex system. As shown in the right-hand side, a graph actually is a very simple data structure. It have a bunch of nodes that essentially try to denote different kind of objects. And the edge that connect the 2 nodes can be think about as relationship between 2 graph nodes, or some kind of similarity between 2 graph nodes. Let's take a concrete example in the information retrieval domain. So suppose that people who today are naturally being using all kind of social network, okay, from the Facebook to the LinkedIn, and people are using YouTube, and we actually formulate all kind of a knowledge graph in this either social network or is a knowledge graph. And we often need to send a query, try to find the information we want, okay, and this intelligent system will return the result based on our personalization information. So when we talk about the deep learning on graph today, we talk about the deep learning graph technique will take two input. One is graph topology information, that is graph structure, as well as any kind of the sign information, such as a node attribute. And then we try to perform the task like node calculation task or link prediction task. That is essentially downstream tasks that we try to tackle. We also can utilize all kind of graph representation feature information, for example, to enhance our search engine, to enhance our recommendation engine. So as you can see that the graph data really is everywhere today, from the internet to the social network. That's actually everything is represented in graph. And in the information retrieval domain, it's clear that everyone is connected. And so as we just explained before, so the graph learning feature can greatly enhance the current information retrieval system. Even in the biology domain, people today have been using graph technique, try to modeling the chemical compound as graph, and then try to learn a distribution of this graph through the variance of the already discovered drug, for example, and then try to generate a new graph with a certain property so that we can accelerate the new drug discovery. People have also using, for example, the data flow graph or control flow graph to do the program analysis. Even in the well-known computer vision domain, if we talk about the high-level reasoning activity through image, people have been leveraging the graph neural nets to do such a task and have achieved a great success. So in the NLP domain, graph is also everywhere. As you can see here, that since the human language is not a simple symbol, it's a high-level symbol that have many underlying structure information. For example, in the previous several decades, people have been studying all different kinds of tool, for example, to analyze the sentence structure, both in the syntactic direction and in the semantic direction. For example, people using dependency graph, people using constitution graph, that to leverage this dependent path tree and constitution tree. People have also tried to modeling a language using AMR graph, that if two sentences are talking about the exact same thing in the semantic space, then the AMR graph should be same. People also can be have been using IE graph to try to analyze the event, high-level event for a sentence. Even in very specific domain, for example, a SQL, people have been using the SQL graph, try to model the SQL querying, since that the different clause, really, they don't really have any order information. It's not purely a sequence. So graph definitely is a better alternative structure to present a SQL. So with all this graph example in NLP, so we will talk about various of the conventional machine learning technique people have been using to apply on this graph for various NLP tasks. So let's first talk about in history how people represent natural language. So at a very early time, so people have been trying to represent the natural language as a bag of the tokens. As shown in the right-hand side, so they have several sentences, and then people have been treated this each token as kind of just a token without any semantic meaning. And they can use it, for example, using bag of word or TF-IDF to represent this sentence to get the embedding for them. However, this is definitely not ideal because some word or sentence, even though that they use a different word token, but they may talk about a very similar thing. So later people have been try to represent the natural language as sequence of token, where people try to train a model to represent each of the word token as a dense vector. The successful technique like word-to-vector and global vector have been demonstrated that it's a very powerful to capture the semantic representation of each word token. And that's why that have been paved the foundation for the modern NLP. As we discussed before, we can also represent a natural language as a graph, because there are many hidden structure information that is behind a given text sequence. Beyond the like all kinds of this graph, like a dependency graph or I graph we discussed before. So even for a very simple idea, for example, as shown in the right-hand side, a text graph, this text is you can think about as a document, and one document can be considered by multiple paragraph. Each paragraph can consider multiple sentences, and each sentence also can have multiple words, right? So with this hierarchy, we can easily to build a hierarchical text graph. So, okay, so yeah, there are many conventional machine learning techniques have been using for the NLP. So we have been pick a 4 representative algorithm that is being extensively studied in the literature. So people have been using like random walk algorithm, which is try to generate a random path so that we can obtain a standardly distribution over all graph nodes. This kind of a technique have been using to compute like semantic similarity of two text, and they can also be using for the name disambiguation task. People also have been formulate a text clustering task as a graph clustering task, so that people may use like spectrum clustering, random walk clustering, and min-cut clustering technique for this task. People also can using graph matching algorithm to some certain number of the NLP tasks, such as text entailment, where we try to compute a similarity between two graphs, and the graph are formulated from the text and hypothesis. People have been often using label propagation algorithm because they can propagate label from the labels, the data point to the previous unseen data point, so that they later can using, for example, for like what sense disambiguation task or sentiment analysis. There have been a book that published in the 2011 by the Mihela and Radev. And so if you are more interested in a more machine learning method for the NLP, please refer to this book for more details. Okay, here today we are with the rising of the deep learning, so we love to talk about the modern machine learning technique, especially deep learning technique on graph. We will talk about the foundations and also various models. So before we talk about that, so let's recap. So what is the machine learning cycle, life cycle? So for any kind of people who already have experience in machine learning and NLP, we all know that feature learning is very important. So before the deep learning, so people have been spending a lot of time trying to doing the feature engineering. That's because that so how to transform the raw data to a structured feature matrix is very important. With the rising deep learning, people have been tend to using a neural network to automatically learn the feature from the raw data, so that we don't have to do any ad hoc feature engineering technique. And then once we learn the representation, we can feed that to the learning algorithm, and then to learn a model, and then to feed it to the downstream task. So similar thing we want to do in feature learning in graph, where our goal here is try to design an efficient task independent or task dependent feature representation learning technique. So as shown in this figure, we try to transform the graph node into its latent space, and to design a function to do this transformation, so that in the latent space we can use a vector to represent a graph node, and this is called a feature representation learning, or could be called embedding. So with the graph neural nets, so we will talk about 2 embeddings. One is try to learn a node level embeddings, other one is graph level embedding. As shown in this equation, so the learning process of the graph node embedding is try to take a graph structure information as well as input node embedding, and then to generate a new node embedding. So the whole process is referring as a graph filtering. And I can see that the graph filter operation is a key to determine the different type of the graph neural nets. We can roughly categorize current graph neural nets method into 4 different groups: spectrum-based method, spatial-based method, attention-based method, and recurrent-based method. And we'll talk about each group in detail in the later slides. One thing to note is that graph filtering don't change the graph structure. It's only update the node embedding. Therefore, so if we want to get a graph level embedding, we have to design another operation to achieve this goal. So that's how people propose this pruning operation, where this pruning operation is try to take a graph structure input and input the node embedding, and then to generate a smaller graph with a few nodes. At the same time, to generate the new node embedding corresponding to the new graph node. In general speaking, we can carry them into two groups. One called the flat graph pruning, where you can use some very well-known pruning operation, for example, max pruning, average pruning, or mean pruning. And we can also use very advanced graph pruning technique, such as hierarchical graph pruning, where the key here is try to leverage a technique called the Cosine technique, try to generate a bunch of the smaller graphs in each layer, and then we can calculate the graph level representation for each layer, and finally to generate a more powerful graph level representation. But in most of the NLP tasks, the flat graph pruning will be enough for most of the tasks. Okay, so now let's using a very basic model, try to illustrate how graph neural works. The key idea here is try to generate a node embedding based on a local neighborhood. As shown in this graph, A is our target node. If we want to learn a representation for graph node A, we need to take advantage of the context information, where we can assume that the first order neighborhood is the context information like B, C, D. Okay, so and then each of the nodes like B, C, D, they can also formulate their own first order neighborhood, treat them as a context information. Therefore, that we can see that every node can define a unique computational graph for themselves. So now let's take a look at what is a neighborhood aggregation. So as shown here that we can have a several layer, try to learn the graph representation. In the first layer, the input graph node will have its own initial node attribute. And conceptually, the depth of the layers could be arbitrary, but in reality, it's not. For example, this really depends on different graph neural net algorithm we have been using. For some well-known algorithm like graph convolutional network, it's well known that it can only use like 2 layers, 3 layers, 4 layers. Beyond that, it have a serious over-smoothing problem. And I want to point out that so the over-smoothing problem, or how to develop a deep graph neural net, is a very active research area in the machine learning community. So once we have that, then we can have some kind of a neighborhood aggregation function, so that we can aggregate these features layer by layer, so that we can propagate the message, and finally try to learn a representation for each of the nodes. Here is an overview for the graph neural model. So first, we have to define a neighborhood aggregation function, so that we can aggregate the message and then to update the node embedding for each of the nodes. And then once we learn the representation for each of node, we can define a loss function on the embedding we have learned so far, respect to the downstream task. And then we can train on a set of the node. For example, we can use a batch of the computational graph to train the model. And then finally, we can generate embedding for each graph node. One thing I have to point out is that since we are not learning the parameter model for each of the graph node, instead we are learning an aggregation function. Therefore, that we can even generate an embedding for the node that the level trained on. This is also called transductive training or inductive training. And here we actually talk about inductive training. So now let's see, so what kind of aggregation function we can use. So here we just give a very simple aggregation function, for example, average neighborhood function, which is just try to average messaging from neighborhood. And then we can apply a neural network and to generate the final result. Here is a basic math behind this whole process. So the purple box here showing that at the very beginning, we only have an initial node attribute. And then we can doing the average aggregation to average the neighborhood layer embedding to formulate a message. And once we have this message, then we can fuse this information with the node embedding from the previous layer. And then we can apply another nonlinear function, try to generate a new node embedding. So as you can see here, the key idea here is try to generate a node embedding by aggregating neighborhood information. This will allow for the parameter sharing in the encoder. At the same time, it's also allowing for the inductive learning. So now we are ready to talk about the popular graph neural model. And as we discussed before, we have 4 different groups that we try to categorize here. The first group is called spatial-based graph filter. The representative methods is graph convolutional network or chip-shape graph neural nets. And another group called the spatial-based graph filter. Here we have a massive passing neural network, and we have graph stage, and recently we have GRN. And the third popular group called the attention-based graph filter. The most representative method is the GAT method, the graph attention network. And finally, it's a recurrent-based graph filter. The representative method is gated graph neural nets. This is actually the first modern graph neural nets that have been developed in the literature. So let's first talk about graph convolutional network. So the key idea here is try to apply spectrum convolution on graph, which can be defined as a modification of the signal X with the graph filtering that is parameterized by parameter theta in the Fourier domain. So in order to do the graph Fourier transformation, we have to perform an eigenvalue decomposition, which could be very expensive when the matrix is large and dense. So therefore that we can, people later have been proposed using chip-shape polynomial, try to accelerate this process. But it's showing promising result, but still not powerful enough. So later in the graph convolutional network, they have been proposed this first order approximation in the Taylor expansion. I have been showing that although it's an approximation, but it's fast and powerful. But this is numerically not stable. Try to directly add the identity matrix with Laplacian matrix. So people have been later apply a renormalization trick, try to stabilize the numerical computation. And this is a modern graph convolutional network. This has been widely used for various of the NLP tasks like graph classification, question answering, text matching, topic modeling, and information extraction. The second group is called massive passing neural network. So the key idea here is that is try to treat the graph convolution as a massive passing process. So there's 2 key functions that have been defined. Aggregation function is try to aggregate all the node and edge embedding and to formulate a message. And then in the later using update function, try to fuse the information from the message and also the node embedding from the previous layer, and then to generate a new node embedding. As you can see that so if the number of the node in a neighborhood is large, then it will be very expensive, especially for a very dense graph. Later, in order to accelerate, in order to address this issue, graph stage method have been proposed sampling, try to obtain a fixed number of neighborhood so that they can accelerate the computation. At the same time, it can often also reduce the overfitting issue. And this both method, MPN and graph stage, have been widely used in the many NLP tasks like a knowledge graph, information instruction, and semantic parser. The third group is called graph attention network. The key idea here is try to dynamically learn the weight. You can think about weight as kind of attention score on the edge. So when they're performing the massive passing. The rationale behind that is all the previous work only treats the graph nodes equally, contribute to the final graph representation learning. However, it perfectly makes sense that the different node may play different role in terms of the importance to this massive passing. Therefore, that the graph attention network try to use self-attention that is inspired by the transformer, try to learn an importance between the target node and this neighborhood. And therefore that later they can perform this weighted sum try to generate a better node embedding. As I mentioned before here, so they use self-attention, try to learning the local weights. Then in each intermediate step, they are using concatenation to generate a new node embedding. But in the final layer, they will try to do the averaging to generate the final node embedding. And the GAT probably is one of the most extensively used graph neural network model in the NLP tasks. People have been widely using in the text classification task, question answering, logic graph, information instruction, and so on and so forth. Okay, finally, the last group is called the gated graph neural nets. So the key idea here is try to using gated recurrent unit when taking into account the edge type and direction. So this method is a little bit special because it can consider the directed graph. At the same time, it will consider the incoming and outcome edge. So at the very step, at the very first step, you can see that the first was zero parting all the input node embedding, that because a different node may have a different dimension of the node feature. And then later, they will formulate a big augmented matrix to take into account both incoming and outcoming edge, and then to generate, to aggregate them to generate a message. And then later they apply get the recurrent unit, try to fuse the information between the message and the node embedding from the previous layer to generate a new node embedding. So as I mentioned before, gated graph neural nets is the first modern graph neural nets. And another special thing about the GGNN is that it can not only generate embedding for a node, but also can generate a sequence of the embedding. And this have been method have been widely used in the semantic parser and the machine translation. Okay, so we have been talking about all the basic foundation about our topic, deep learning on graph for NLP. Let's part, we will talk about the key foundation for the DLG4NLP. We'll talk about the graph construction, where we have static graph construction method, dynamic graph construction method, and also we can also have a hybrid graph construction method. Once you have a graph at hand, later we have to choose what's the proper graph representation learning technique to use. That really depends on it's a static graph or dynamic graph or is a Heterogeneous graph. And finally, we will talk about the encoder decoder framework that is based on the graph method. We'll talk about the graph to sequence method. We'll talk about the graph to tree method. We'll not talk about the graph method because this is still under very active development. And later we will talk about the variance applications that people have been trying to leverage the graph neurons in their domain. Okay, that's all for the graph analogy. This is the roadmap. Next, I will pass the level flow to my friend Yuchen.
Hello, everyone. My name is Yu. I'm a research scientist at Facebook AI. Now let's move on to the DLG4NLP foundations part. Let's first talk about the graph construction for NLP. While graph construction for NLP, as we previously introduced, there are three typical ways of representing text, which are back, sequence, and a graph. Among other three approaches, graph has the strongest representation power because it can capture rich and diverse information about the text. We know that different NLP tasks require different aspects of text, such as syntax, semantics. In the meanwhile, different graphs capture different aspects of the text. Therefore, how to convert a text to graph is an important yet a challenging question, which really depends on what aspects of information we want to capture in a text graph. In general, we group variance graph construction approaches into two categories: static graph construction and dynamic graph construction. We will introduce each of them and summarize their properties next. Note that the primary goal of graph construction we are talking about in this tutorial is to achieve good downstream task performance. Let's first talk about the static graph construction. It aims to convert the raw text to a graph where text can be sentence, paragraph, document, or corpus. It's usually conducted during the pre-processing stage by augmenting raw text with various domain knowledge, including syntax, semantics, topic, co-occurrence, word knowledge, and so on. Many of them are actually quite application-driven. The first static graph construction approach we are going to introduce is dependency graph. Dependency parsing is widely used to capture the dependency relations between different words in a sentence. For instance, given a sentence, are there other jobs outside Austin? One can apply dependency parsing tools to convert it to a graph like this. But what if we have multiple sentences in text? One common way is to add additional sequential edges between nodes so that we can connect multiple dependency graphs in a paragraph. Besides, it also reserves sequential information in raw text, which can be helpful in some applications. The next approach we will introduce is Constitutive Graph. The Constitutive Graph is able to capture phrase-based syntactic relations in a sentence. For instance, given a sentence, one can apply constitutive parsing tools to convert it to a graph. Due to the same reasons, one can add additional sequential edges between nodes. The AMR graphs are widely used to represent the high-level semantic relations between abstract concepts of text. Different sentences that are semantically similar may share the same AMR graph. Given a sentence, Paul's description of himself, a fighter, one can apply AMR parsing tools to convert it to a graph. The IE graph aims to extract the structural information from text to represent the high-level information about entities and their relations. Given the input text, one can apply IE tools to convert it to a graph which contains entities such as Seattle as nodes and the relations such as attended as edges. Coreference resolution is usually conducted to group entities referring to the same concept to a single node. Like here, Paul, he, and a renowned computer scientist refer to the same person. The knowledge graph stores word knowledge about entities, their relations. Given a question, who acted in the movies directed by the director of some other sum, one can first identify the topic entity of the question, which is some other sum, and then extract a subgraph from a knowledge graph which surrounds the topic entity and hopefully contains the answer entities of this question. Topic is the subject that the text is about. One can find the connections among multiple sentences of documents by connecting them to a shared set of topics. Another way to find the connections among text is to compute their pairwise similarity scores. And one common way to compute the similarity scores is to first embed the text into some vector representations such as TF-IDF vectors, and then compute their pairwise similarity in the embedding space. In order to capture the word co-occurrence information, one can regard the co-occurrence matrix as an adjacency matrix, and then construct a graph containing each unique word as a node. Some logical form, such as SQL query, can also be naturally represented as a graph, which will capture the relations among variance objects. There are also variance application-driven graphs which augment text with rich information and are highly coupled with a specific NLP task. As we already seen, static graph construction operates by augmenting text with variance domain knowledge during preprocessing, including syntax, semantics, topic, co-occurrence, word knowledge, and so on. For each type of domain knowledge, there are various types of graphs we can construct, which usually depend on the specific application. As we will see in the application part of this tutorial, these static graph construction approaches are widely used in various NLP applications, such as NLG, reading comprehension, and semantic parsing. Next, we will introduce dynamic graph construction, which shares the same goal with the static graph construction. Unlike a static graph construction, which is performed during preprocessing, dynamic graph construction operates by jointly learning the graph structure and the graph representation on the fly. The ultimate goal is to learn to optimize the graph structures and the representations with respect to certain downstream prediction tasks. We summarize the typical dynamic graph construction pipeline as follows. Given a set of data points, which can stand for various NLP elements such as words, sentences, and documents, we first apply graph similarity metric learning, which aims to capture the pairwise node similarity and returns a fully connected weighted graph. Then we can optionally apply graph specification to obtain a sparse graph. If the input data is instead of data points, but an intrinsic graph containing edges, we can also optionally combine the intrinsic graph and the learned implicit graph to form an augmented graph. The output graph will be consumed by a subsequent GN-based module to learn graph representations and predict outputs. Next, we will introduce each of the 4 dynamic graph construction techniques, which we summarize from the existing practice of its applications in the NLP field. These include graph similarity metric learning techniques, graph specification techniques, combining intrinsic graph structures and implicit graph structures, and learning paradigms. The idea of graph similarity metric learning is to compute the pairwise node similarity in the node embedding space and obtain an adjacency matrix based on that. It can enable inductive learning because once the similarity metric learning is finished, one can apply it to unseen nodes to learn a graph. This is important for many NLP applications because we want to learn a new graph for each new text example. Variance metric functions have been proposed by previous works. We group them into 2 categories: node embedding-based similarity metric learning and structure-aware similarity metric learning. For node embedding-based similarity metric learning, we are given a set of data points and their vector representations, and apply variance metric functions to learn pairwise node similarity. The output is the weighted adjacency matrix, which is corresponding to a fully connected weighted graph. Common metric functions include attention-based and cosine-based functions. Let's talk about attention-based similarity metric functions. In variant 1, Vi is node embedding, and U is a non-negative weight vector learning to highlight the different dimensions of the node embeddings. In variant 2, W is the learnable weight matrix, which maps the node embeddings to a latent space, and the ReLU activation functions is used to enforce the sparsity of the similarity matrix. In both variants, dot product is used to compute the similarity. Let's see an example of cosine-based metric function. Here, WP is the weight vector associated to the P's perspective and has the same dimension as the node embeddings. Intuitively, SIGP computes the pairwise cosine similarity for the P's perspective, where each perspective considers one part of the semantics captured in the embeddings. One can average multi-header similarity scores to increase the learning power of the metric, which is similar to the idea of multi-head attention in transformer-like models. Now, let's talk about structure-aware similarity metric learning. Unlike the node embedding-based metric learning, this metric learning approach, in addition, considers the existing edge information of the intrinsic graph when it's available. Let's see 2 example metric functions. So in these 2 variants, attention-based function is applied at a notably edge embeddings of the intrinsic graph play an important role in learning the implicit graph structure. So far, similarity metric functions learn a fully connected graph. However, fully connected graph is computationally expensive and might introduce noise. We might want to enforce sparsity to the learner graph structure to obtain a sparse graph by leveraging variance techniques, such as what we list as follows. For Kn style specification, for each node, only the k nearest neighbors, including the node itself, and the associated similarity scores are kept, and the remaining similarity scores are masked off. For epsilon neighborhood specification, those elements in the similarity matrix which are smaller than a non-negative threshold epsilon are masked off. So besides explicitly enforcing the sparsity of the learner graph by applying certain form of threshold, sparsity can also be enforced implicitly in a learning-based manner. For example, one can apply certain form of graph regularization to the learner adjacency matrix. The intrinsic graph typically still carries rich and useful information regarding the optimal graph structure for the downstream task. Some recent works proposed to combine the learned implicit graph with the intrinsic graph structure based on the assumption that the learned implicit graph is potentially a shift from the intrinsic graph structure, which is supplementary to the intrinsic graph structure. One common way to do this is to compute a linear combination of the normalized graph Laplacian of the intrinsic graph structure and the normalized adjacency matrix of the implicit graph structure. And we can apply variance normalization operations to the learned adjacency matrix, such as graph Laplacian and raw normalization. Now let's talk about some important learning paradigms for dynamic graph construction, which have been explored so far. Most existing dynamic graph construction approaches for GNNs consist of two key learning components, graph structure learning and graph representation learning. The most straightforward strategy is to jointly optimize the whole learning system in an end-to-end manner toward the downstream prediction task. Another common strategy is to adaptively learn the input graph structure to each stacked GN layer to reflect the change of the intermediate graph representations. So this is kind of similar to how transformer models learn different weighted fully connected graphs in each layer. Unlike the above two paradigms, recent work proposed an iterative graph learning framework by learning a better graph structure based on better graph representations, and in the meanwhile, learning a better graph representations based on a better graph structure in an iterative manner. As a result, the iterative learning paradigm repeatedly refines the graph structures and the graph representations toward the optimal downstream performance. And the variance stopping conditions can be applied for the iterative learning process. For example, one can stop the iterative process when the difference between learned adjacency matrices at consecutive iterations is small enough. So far, we have introduced the variance dynamic graph construction techniques, including graph similarity metric learning, graph specification, combining intrinsic and implicit graph structures, and the variance learning paradigms. One might ask, how is statical graph construction compared with dynamic graph construction? Which is better? Let's first talk about the statical graph construction. The biggest advantage is it can easily encode rich prior knowledge in graph, which can be very helpful for certain NLP applications. But this can also become a downside when it's expensive or not doable to obtain such extensive domain expertise. For example, for some low resource languages, well, we might not have rich prior knowledge to utilize. Besides, static graph construction is error-prone due to noise or incomplete graph, and therefore is often suboptimal. Due to its disjoint graph construction and the representation learning nature, it can also lead to error accumulation. Compared to static graph construction, dynamic graph construction is quite new and has not been extensively studied in the DLG4NLP area. Its advantages include requiring no domain expertise and the joint learning of graph structures and the representations. Currently, it has some disadvantages such as scalability and explainability, which are actually also some good future direction in this topic. Now it comes to the question, when to use which? Based on our study and practice, it's best to use static graph construction when we have domain knowledge at hand, which fits the task and can be represented as graph. For dynamic graph construction, here might be some reasons why we want to look into that, including lack of domain knowledge, which fits the task or can be represented as graph. Domain knowledge is incomplete or might contain noise, or we want to learn implicit graph, which augments the static graph. Actually, we think the last point is a big advantage of dynamic graph construction, since we can combine the benefits of both intrinsic static graph and the dynamically learned implicit graph. Now let's move to the next part, graph representation learning for NLP. Let's briefly recap on the DLG4NLP pipeline. Given a graph, we will need to decide which GNs to apply for graph representation learning, and we will try to help answer this question in this part. Let's first review some definitions on various types of graphs. Those concepts are important since we will mainly depend on graph types to choose which GNs to apply. So when the number of node types is 1 and the number of edge types is 1, we call the graph as homogeneous graphs. And when the number of node types is 1, but the number of edge types is larger than 1, we call it multi-relational graphs. And when the number of node types is larger than 1, we call the graph heterogeneous graph. Let's first see the overall roadmap on which GNs to use given a graph. This works like a decision tree, which we summarized to help you make this decision. In short, we will decide whether to apply homogeneous graphs, multi-relational graphs, and heterogeneous graphs based on the input graph types. When to use homogeneous GNs? Given a graph, if it's a homogeneous graph, then we can simply apply homogeneous GNs. Or it's not a homogeneous graph, but we can convert it to a homogeneous graph via variance techniques. Then we can also apply homogeneous GNs to the graph. And homogeneous GNs include many of the GN variants which we have introduced in the introduction part, including GCN, GAT, GraphSage, GGN, and so on. Given a non-homogeneous graph, which contains various edge types, we can leverage Lavie graph conversion to convert it to a homogeneous graph. Then we can simply apply homogeneous GNs to the graph. So the key idea is to regard each edge in the original graph as new nodes and connect original nodes and new nodes. As a result, we will get a bipartite graph. We know edge direction is important. Just think about the success of BiSTM and BERT. Given a directed graph, we might not be able to directly apply some homogeneous GNs, which will lead to edge direction information loss. Common strategies for handling directed graphs, including message passing only along directed edges. So we can use GAT, GGN, and so on to do this. But that might lead to edge information loss still. The second strategy is to regard edge directions as edge types. And the third strategy is to apply bidirectional Geons. We will introduce the later two strategies next. Regarding edge directions as edge types will result in a multi-relational graph. For example, we can keep all the original edges in the graph and regard it as a default edge type. And we can also add inverse the edges to the graph, and the corresponding edge type is inverse. We can also include self loops to the original graph, and their edge type is self. Now let's talk about the bidirectional GNNs for directed graphs. We summarize two variants of bidirectional GNNs. The first one is called the bicep GNN. Bicep GNN works similar to the famous BiSTM model. It first runs multi-hop backward and forward GNNs on the graph. And then it concatenates the backward and forward node embeddings at the last hop. The second one we will introduce is called the bifuse GNN. For bifuse GNN, it will first run one hop backward forward node aggregation. And then it fuses a backward forward aggregation vector at each hop. Then it updates node embeddings with the fused aggregation vectors at each hop. And one can stack multi-layer bifuse GNNs. Now let's talk about multi-relational GNNs. When to use multi-relational GNNs? Given a graph, if it's not a homogeneous graph and it contains only single node type, then it's a multi-relational graph. Then we can apply multi-relational GNNs. Or we want to convert it to a homogeneous graph, but it's a directed homogeneous graph, and we want to regard edge direction as edge types. Then we will finally get a multi-relational graph. Then we can also apply multi-relational GNNs to the graph. And multi-relational GNNs have various types of architectures. We summarize the three common variants, which either includes relation-specific transformer parameters in GNN, includes edge embeddings in GNN, or its multi-relational graph transformer. So RGN is the most common variant which works like this. It has two features. It introduces relation-specific transformation. For example, the node feature transformation attention weight, and it does aggregation per relation-specific subgraph. When we apply the RGN idea to GCN, we get RGCN. As you can see, it introduced relation-specific D by D learnable weight matrix. RGN is good at doing relation-specific message parsing, and hence is able to handle multi-relational graph. However, it's kind of expensive to learn D by D transformation weight matrix for each relation, and that's especially true for some graphs with a large number of edge types, such as KG. So how to avoid over-parameterization? There are two common ways. One is to introduce bias decomposition, which regards the relation matrices as a linear combination of shared bases, which can be seen as a form of weight sharing between different relations. The second strategy is block diagonal decomposition, which can be seen as a matrix sparsity constraint. The second type of multi-relational GNN explicitly includes edge embeddings in GNNs. Let's see two variants of that. So in both variants, edge embedding EIJ participate into the node aggregation process. Compared to variant 1, variant 2 also updates the edge embeddings at each GN hop. The third type of multi-relational GNN we will introduce is multi-relational graph transformers. Let's first talk a little bit about transformer models. Actually, transformers can be regarded as a special class of GNNs which jointly learn and encode a fully connected graph via self-attention. They share many similarities with GAT. However, the vanilla transformer models fail to effectively handle arbitrary graph-structured data. Multi-relational graph transformers aim to combine the benefits of both typical GNNs and the transformer architectures. They usually employ structure-aware self-attention and respect the variance relation types. Let's talk about the two examples of multi-relational graph transformers. RGAT-based graph transformers employs the GAT-like mask attention, which respects the graph structure of the input data. It also introduced relation-specific learnable weight matrix, which respects the edge type information. The structure-aware self-attention-based graph transformers introduces edge embeddings that participate into both the self-attention computation and the node aggregation process. When to use heterogeneous geons? Given a graph, if it's not a homogeneous graph and we don't want to convert it to a homogeneous graph and it contains more than single node type, then it's a heterogeneous graph and we can apply heterogeneous geons to encode the graph. We will introduce one popular variant of heterogeneous geons, which is based on the middle pass idea. Let's first see one example of middle pass. So here we show two middle paths between the author nodes. For example, the author can write a paper which mentions a topic, and the topic can be mentioned by another paper which is written by another author. And besides that, the author can also write a paper which publishes a venue, and the venue can publish other papers which is written by other authors. So these just two examples of the middle path between the author nodes. Below are three key steps of middle path-based heterogeneous geons. The first step is to apply type-specific node feature transformations. And the second step is to do node-level aggregation along each middle path. And the third step is to do a middle path level node aggregation.
Previously, Yushen had been talking about a variance graph construction method. And once you have a graph, what graph reinforcement learning technique you should choose. So in this part, I will continue to talk about the graph-based encoder-decoder model for NLP tasks. So as we all know that the sequence model have been achieved a great success in various applications. The key part of the sequence model is to take a sequence input and then try to learn a mapping between the sequence input and sequence output, so that it can translate the original input sequence to the output sequence. There have been a lot of applications, such as machine translation, natural language generation, logic form translation, even the information extraction. However, there are multiple challenges here. First of all, based on the input structure, this can only apply to a problem whose input represent as a sequence. But in real problem, there are many tasks that we are not only consider the sequence input. The input could be much complex structure input. Therefore, in this case, so we cannot directly use this model to handle this situation. But just as we mentioned before, right? So there are so many hidden structure information that is behind the text sequence. And once we add this graph input, this hidden structure input as a graph, so there's no way to leverage the existing sequence model to do this translation anymore. Therefore, that people may consider to converting a graph input back to the sequence that may lose information. So in this motivated by these challenges, so we have been proposed gradual sequence model that essentially is consists by a graph encoder and a sequence decoder. So the basic key idea here is try to using a graph encoder, try to encode the graph input, and then we will here there's a subtle difference between the previous work is that so we are not only consider the unidirectional graph embedding, we are also consider the we try to split the edge information between incoming and outcoming edges, so that we can learn the representation separately for both direction. Just like by STM over the advantage of this is just like advantage by STM over the LTM. And once we learn this bi-directional node embedding, we have to compute the graph level representation so that we can use a single graph level vector to summarize the whole graph, and then to feed that to a decoder. And decoder will use this as the initial content information and starting decoding. As we all know that also the attention will be very important. Otherwise, without attention, the sequence decoder performance will be degraded a lot. So therefore that we have this attention-based sequence decoder so that we can do a good decoding. They have our previous paper to talk about this gradual sequence model. And now let's take into account into the details. So previously, you should have been introduced a lot in detail about the bidirectional graph units for the directed graph. So here we will skip the details. And this is another variant of our bidirectional graph units using bi-fuse method. So as I mentioned before, so once we learn the graph level, node level embedding, we have to generate a graph level embedding so that we can feed that to the decoder. There are basically two different type of methods to do that. The first method is called pooling-based graph embedding, where we can using like a max pooling or min pooling or average pooling. The second method is called the node-based graph embedding. The key idea here is that they try to insert called a super node that into a graph so that this node is connected to all the graph. And then we can just run normal graph neural nets method and then to using the embedding of this super nodes, treat them as a graph level embedding. However, this is useful, but often perform poorly compared to the pooling-based graph embedding. The reason probably because that so this artificial insert a super node will change the original graph structure, therefore that bring noise into the original graph. Therefore that the performance of that is degrade compared to the pooling-based graph embedding. So as we know, attention is very important for the sequence decoding. So here we just introduce a very simple attention mechanism here. Is that when we treat the graph as a homogeneous graph, okay, and every node type are the same. Therefore, that we can compute the attention, and then we can maximize our objective function. That is try to maximize the local probability distribution when we decoding the current token, given that the already decoded token and the input sequence. Here we're showing some task results when we try to examine the impressive power of our graph to sequence model on the two tasks, text reasoning and the shortest path. And we can see here that the text reasoning here we choose a baby task T19 task. So this is a task that introduced by Facebook around 2015 or 16. And original purpose try to test the reasoning capability of a current deep learning approach. And like, as you can see here that so there are multiple sentences that lead a model try to reasoning over the sentence in order to get the answer. So with this information, we can format a graph and then finally try to generate a path. For example, how do you go from the bathroom to a hallway? The other tasks that have been tested here is called shortest path task. that is purely only leverages the graph structure information, and we try to generate a path, a shortest path from the destination, the original location to the destination location. As you can see here that on the baby task, all graph-based methods can significantly outperform the LSTM-based method. But our method, graph sequence, since we are using bidirectional node representation, we are actually achieve better performance compared to the gated graph and the GCN baseline. In the sorted path task, so we have divided them into two different subtasks. One is a graph with a smaller graph, another one with a large graph. And we believe that when we increase the graph size, so the difficulty problem increase as well. As you can see that indeed when we on the small graph, every graph-based method perform very similarly, but when we increase the graph size, our bidirectional graph embedding can perform much better. So here is another plot try to show the effect of the bidirectional node embedding. As you can see that here that the bidirectional node embedding indeed can converge quickly. That's because we will learn the representation from both directions. But we can also see that when the number of the hops increase, finally the unidirectional node embedding will perform similarly to the bidirectional node embedding because they already learned all the constant information through the graph. Okay, now talk about so when shall we using our gradual sequence model? The first scenario we should consider that so if input is laterally represented in graph, then in this case that we should using our gradual sequence model. Just as shown in this NLP task, this task called is AMR to text. This task is M to generate the text diffusion giving AMR graph. So another scenario I think is more important is that so we can generate this hybrid graph with sequence and its hidden structure information, just as we have been intensely discussed in the graph construction part. So therefore that we can combine the domain knowledge with the current sequence. In this case, that so once we formulate graph input and have a sequence output, we should leverage our gradual sequence model. Well, even further, so sometime we are consider not only the graph input and the sequence output, we are consider input output the structure input output. As shown in this right hand table, so we have two different tasks. One is a semantic parser, one is a math word problem. As you can see here that so the text input is a text sequence, but as we mentioned before, we can leverage the hidden structure behind that. Therefore, that we can formulate them as a graph. But in the output side, it's not a simple sequence. It's essentially a structured output. Both the semantic parser or this SQL language or this word math equation, essentially it's not a simple sequence. It has the very clear structure information which can be represented as a tree. And that actually is better represent the output. In that case, so essentially it's a structured output. And therefore that we are really trying to learn a structured input-output translation in this NLP task. So currently, so this here is just some simple demo to show what kind of graph construction we can do for the text sequence input and what kind of tree construction we can do, for example, for the math equation. So for the tree decoding, obviously, we can have two different types of the decoding. One is the depth first search-based tree decoder that we first search the tree along the depth, and then we try to go to the left side. Another one is breadth based search and for the tree decoder. So this one actually we can leverage multiple information. For example, the sibling feeding information. Therefore, that so in current our later model we have been leveraging this technique. So here we have been showing our proposed Gradual tree model. This is the overall computing flow for that. So we have this input, and then we can using dependent path tree to augment the kind of input to formulate a graph, heterogeneous graph input for our graph encoder. And here we have this bi-directional node embedding, try to generate node representation for each graph node. And then we can do the pooling to feed it to the tree decoder. One of the important part that compared to the previous quantum sequence model is that so that the attention module is actually have a lot of choice. That really depends on the type of the graph. For example, in this case, so our graph is a heterogeneous graph, therefore that the different node may have a different type. In that case, that we can have this separate attention, try to attend to the different type of node using one attention mechanism. And then we can put them together to generate the final context vector information, and then to do the decoding. As we mentioned before, here decoding, we consider both the symbolic fitting, parent fitting, and all this information will be taken into account when we do the token decoding. And have been showing that so this is quite an important factor. So here I have some details information about the separate attention based tree decoding. So first, we will generate the context vector embedding for the different graph node, and then we can. So here, the most important part, how to compute the separate attention weights, and finally, we will generate the final attention hidden state and use this to decode the tree. So here is just a simple result showing that compared to the current state-of-art mass word problem baseline, and one thing I want to point out is that so all the existing state-of-art, they try to doing some called equation normalization technique. That is essentially try to normalize normalize all the mass equation into one single form. This is not really good because the reason that we're doing the mass word problem is trying to show you the reasoning process about how human beings think about the problem and then to write their own mass equation. So if we do the normalization, we will lose all this intermediate process of the reasoning process. So in our Gradual tree model, we don't do any equation normalization. We firstly to generate the original mass equation so that we can preserving a meaningful explanation about how we construct this equation. And as you can see that, so this is very remarkable, even though that we don't do any pre-processing, just using our Gradual tree model, we can achieve the current state-of-art performance use a different graph construction method. And based on we can also see that when we change the different data set, we can still achieve observe very similar result. So this is very encouraging that indeed to highlighting the importance of learning the structure input-output translation using our Gradual tree model. Here's some visualization of the separate attention. As you can see here, that so when we use attention for the word node, indeed, so some of the word node can be captured. That is essentially highly related to the decoder token. And attention also is important for the structure node that is constructed from path tree, and that will also contribute a lot to the final result. And this is very encouraging that so our attention are able to capture that. And so now we will have a half-hour break. So during this process, you can prepare for our demo session. So you can go to this library to git clone our demo code, and then you can follow the get started instruction in the README. Here is also a bunch of the reference for our Gradual NLP library and demo and literature. And then we'll see you in the next part, the second part, our Gradual NLP tutorial. Thank you.
Hi, everyone. I would like to talk about the first application of deep learning from graphs, which is information ingestion. Information injection is naturally a graph learning framework because we normally try to encode a sequence, which is a sentence, paragraph, or document, and then we try to decode the graph out of this sequence. So this graph normally has nodes that are representing entities, and then edges that are connecting the entities or showing the roles of the entities playing in certain events. I would like to show how we can use graph learning to not only improve the quality of injection, but also try to improve portability. So portability, I will talk about how can we transfer information injection model trained from one language and apply to another language, or trained from one data modality, apply to another data modality. And then finally, I also want to mention that graph learning algorithms can help us extend the scope of our problem from not just injection, but also to prediction and also misinformation detection. So let me talk about the first direction of using graph learning algorithms for improving the quality of information injection. So the traditional way to use deep learning for IE is to encode a sequence as input. So here, for example, every token in this sentence will have their own embedding representation, and then we can use a bin search algorithm to decode a graph from this sequence. So in this graph, you can see every token can be a candidate entity or a candidate trigger of an event. And then the edge usually indicates the relation between entities or the argument role this person or this entity played in this event. So very recently, there's some work trying to replace the encoding part from sequence encoding to graph encoding, which means if we can apply some symbolic semantic parsers, such as dependency parsers or abstract meaning representation parsers to encode a graph of the sentence, then we can do graph encoding, then graph decoding. So this is one paper from NACO this year, just a few weeks ago. They tried to capture the interdependency among instances. For example, all of these entities are involved in this event called a cane, and then they encode this graph based on dependency parsing, and then the problem of IE just becomes decoding another information graph from this dependency graph. And another very similar work from my group, also published at NACO this year, is called graph encoding and graph decoding. So the only difference here is that we use a AMR parser that can capture more relation types compared with dependency parsing to encode the input sentence. And the interesting thing is, if you look at the AMR graph on the right side, they are very similar to an IE graph. They look more like a superset of IE graph. So our task naturally becomes, how can we identify the important subset of nodes and edges from AMR graph that match the target ontology? For example, if we're looking for an attack event, a murder event from this sentence, then these highlighted nodes in the AMR graph should appear in the final IE graph. So this inspired us, maybe we can first convert every sentence into a graph using semantic parser, and then we can do graph decoding on top of the encoded graph. So for example, here we can use the AMR parser to convert the sentence into a graph like this. And then we can identify the candidates from the original input sentence for entities and roles in each event. And then we can do graph decoding. So the graph decoding idea will be very similar to what we have already talked about in search, and I will talk about that later. So for graph encoding, we consider every candidate, entity, and event from the AMR nodes, and then we represent them using a edge conditional graph attention network to incorporate information using message parsing from the neighbors of each node. So for example, here, the initial representation of each node coming from the any contextualized embedding, such as BERT embedding, and then we can, using the AMR graph, to parse messages so that every node embedding can be updated iteratively. And now from this encoded graph, we try to decode an information graph that match the target ontology. So in the traditional bin search, what we normally do is we scan the sentence from left to right. Instead of doing that, we are going to scan the graph from top to down, which means if we already identify, for example, a trigger of event, then when we're looking for the arguments associated with that trigger, we don't have to look at the branches or subgraphs in other branches. So basically, for example, we are looking at this trigger number 1. When we are looking for arguments associated with the trigger number 1, we only need to look at this subgraph and we can ignore this part of the graph. So the decoding is done in a top-down manner. I'm just trying to show you some good results compared to this sequence-to-graph traditional framework. We can see that our graph-to-graph model usually can capture long distance. For example, in the first sentence, the entity Washington is far away from the trigger airlifting. So the sequence-to-graph model missed this as entity as argument, but our graph-to-graph model successfully identified this as agent of this event. And these are just some other examples. So that shows that if we have this graph encoding and graph decoding, usually it can give us better quality of extraction results. And now that's only applied for English, right? So now let's talk about how can we further leverage the graph structure to improve the portability to transfer IE from one language to another. So the basic idea is very simple. We can, if we can convert sentences in other languages also into some graph structure. For example, universal dependency parsing is a great tool to convert many languages into the same unified graph structure. And the cool thing is that for IE problems, in many cases, if you look at the connections between two entities that are involved in the same type of relation event, the path in the graph usually looks identical. So for example, on the English side, you can see this connection, which is noun, subject, passive, and object connecting these two entities. And these two entities are involved in a located relation. On the right side, it's a Russian sentence, and this Russian sentence is not a parallel sentence with the English one, but it also has a located relation between two entities. So you can see from the universal dependency parsing output, the connection between these two entities is the same as what we have seen in the English side. So that means if we can map these two graphs into one common semantic space, then we can simply train a model from English training data, then apply that to Russian or any other language, any languages. So to do the encoding, we try to use graph convolution network because it can fit into this encoding very well, the graph structure, and also it's very efficient. So we initialize every node using multilingual embedding. And then because the edges follow the same symbolic representation from universal dependent parsing, we can then propagate the representation from neighborhood to every node to update it. So for example, in the previous layer, you will have the initialization of the each node. And then in the next layer, we try to update that representation using the neighborhood information. So the application of this encoding to any kind of graph decoding problem, such as event argument row labeling, we simply look at every pair of trigger and entity mention and classify that link into one of the predefined event argument rows, or it's not event argument. So that means we can just take every pair of trigger and entity in the graph and do the classification based on the graph encoding representations. So putting this together, we can see that we simply merge the English training data and the Russian sentences in the test phase into a GCN, and then we train the model from the English training data, because English side we do have a manual annotation, and then apply that model to the Russian sentence. We did experiments on English and Arabic because we have ground truth for them. So this figure shows performance for Chinese. If we train a model from English and then do this graph transfer to Chinese test data, we can get about 59% F score, which is very close to 59.2% F score that you can normally get from a supervised model trained from 3,000 Chinese event mentions. So inspired by this success, we further want to do cross-media transfer, because if we consider images and videos as another foreign language, maybe the same idea should work. So the goal is to populate a multimedia event knowledge base using multimedia data, because a lot of information in news is encoded in images, not in the text side. For example, here for this movement event, we can see the vehicles are only shown in the image, but not in the body text. So the idea is very similar to what we have already talked in cross-lingual transfer. We simply take millions of image and caption pairs, and for every image, we try to encode the image into graphs. So we use two different ideas to do that. The first one is to use object detection trained from the existing object annotation from the computer vision community. And then we also use a parser called situation recognition parser, which is very similar to what we normally do in NLP on FreeNet parser. So they select 1,000 frames, and then they can pass each image into a coarse-grained semantic parser. But of course, this kind of symbolic semantic parser does not have enough coverage. So we decided to add another kind of graph, which is called attention-based graph. So we looked at the attention heat map that's associated with each object. For example, this part is aligned with agent. This part is associated with item. And then we merge these two graphs using GCN. For every caption sentence, we again apply AMR parser to convert that into an AMR graph. And then we combine that with the original sentence using BioSTM, and then we can map these two graphs into one common space across data modalities. So in this common space, you can see that this heat map is likely to be aligned with another term called protester in text. And this part, bus, maybe is very close to another vehicle entity in the text. Once we have constructed this common semantic space across image and text, we can then merge the training data from NLP. For example, this is the data for text only, and this is the training data for image only. We can merge them using this common semantic representation and then apply that model to a new multimedia news article. For example, has this image and body text. So using this kind of multi-modal structured common semantic space, we are able to fix a lot of errors, which are very common in the single data modality models. For example, on the left side, if we only look at the image, many image systems will mistakenly identify this as a protest event. But if we look at the text side, clearly it says it's a very happy parade. So our common space was able to fix this error. Similarly, on the right side, if we ignore the image, the text-only system will miss this event because search is not a common trigger word for arrest. But using the common space, that integrate information from multiple data modalities, we can successfully identify this as a REST event. So doing the representation across data modality, this idea is not new. There's a lot of ideas going on trying to integrate multimedia embedding, but most of the previous work did not look at the graph structure. So we also compared with what we call as a flat embedding that does not have the graph encoding part. So you can see in those multimedia embedding representation, they often misclassified many event argument roles. For example, this person was mistakenly identified as an agent instead of person who is being arrested. And especially when we have a bounding box that's very busy, a flat representation will also mistakenly miss that kind of roles. All right, so that shows that graph structure can help us improve the portability. Finally, I would like to talk about how can we use the graph learning to define new problems or more exciting problems beyond IE. So the previous methods I have introduced, most of them are focused on sentence level. So you take a sentence as input and you try to decode the graph. But that's not how humans read or comprehend news articles. Normally, we try to decode the whole knowledge graph on top of a corpus. So we often used what we learned from historical data. So in IE, we can learn this kind of patterns from historical data or what we call as event schema. So the idea here is, can we try to move away from entity-centric natural language understanding to event-centric natural language understanding by induced schema from corpus level? And then we can apply this to improve injection and maybe even use this to predict new information. So event schema will look like a graph structure. Every node is event type, and then you can see different types of connections between events. We can have a temporal relation, causality relation, and a sub-event relation. And we also can induce probabilities to transition from one event to the other. So I would like to first quickly show how can we do this induction and then show how can we use the schema to improve IE and also define new problems. Let's take a look at the connections between every two events first. So every two events, they can connected by many different ways. They can be either connected because they have a temporal relation or because they share some entities. For example, here, this person who is artifact of movement is also attacker of this attack event. Or their entities are involved in some relations. For example, this agent of this movement is the owner of this artifact of this vehicle that's served as instrument for the attack event. So our idea is try to flatten the graph into multiple paths and then rank them based on their salience and coherence. So salience simply check how many instances are being covered by this path. Coherence means that when this path appears together with another path to cover the same documents, they should be coherent. So that means there are many, many documents showing these two paths are co-occurring. So to compute the probabilities for salience and coherence, we adopted the idea of language model, but we consider every path as a sequence and then do mask language model to compute the probabilities. So from this event schema induction, we'll be able to get a lot of global patterns. So for example, one path will tell us that the person who was artifact of transportation is likely to locate in the destination or the attack place. So using that, we can identify a lot of missing links. For example, in this sentence, initially the baseline sequence to graph or graph to graph sentence level model missed this located in relation because two entities are far away. But we use the schema knowledge, the system can successfully identify this link. So the performance of relation projection can be improved dramatically using the graph schema. Okay, so that's about the graph schema between every two events. How about we extend this to the whole scenario? For example, after a person who learned how to assemble a bomb. They can go ahead to purchase some materials, and then they can make the bomb, and then maybe they place a bomb, and then they will be arrested, and there's some investigation events. Maybe there are some die and injury events following that. So the idea is that we can use graph generation model, as we described in the previous sessions, to generate a graph and predict future events. We will start from a few events that we already observed from the data, and then we can predict what's going to be the next node. For example, next node is likely to be arrest node, and then we can predict further what is the link connecting the arrest and the die, and then what are their relations between the arguments, and then finally, what is the temporal order between this event and the previous node? Is this event happening after or before the previous node? So we did experiments by hiding all the ending events and then ask the model to predict them. And we compare the predicted events with the ground truth. So looking at the results, you can see that compared to the human schema-based prediction, our model predicted more events, and also they are more reasonable because, for example, in this case, this person was not arrested yet, so we should not predict anything like sentence or trial hearing. But our model successfully predicted events like die and injure. And another advantage is because it's a probabilistic model, so we can produce multiple hypotheses, so it can have a higher coverage. So you can see the prediction accuracy is much higher than human schema-based model. Okay, finally, I would like to talk about another application, another new problem that can leverage the graph models, which is missing information detection. So information pollution is a huge issue because human is always very good at connecting dots. And when they comprehend different news documents, they usually, or social media posts, they usually try to construct knowledge graph in their mind and then connect dots. For example, here, this woman soldier was falsely accused as patient 0 of COVID-19, even though she was never tested as positive. So the reason is because she traveled to Wuhan in October, and then she came back. So if you look at all these connections, it's likely to convince any audience that maybe this is some true information, right? So that's how fake news was created. Since we cannot interact, so I'm not going to do the quiz, but I'm just trying to show you several examples about how fake news was created. So for this pair, the right side is a fake news. So you can see compared to left side, the authentic news, there are some made up facts. For example, this organization is not founded by this entity, and this person does not have a relation with another person, and so on. So oftentimes the captions of images are always manipulated, and they show fake information. For example, here from this image, it's not clear whether these soldiers are leaving this place or just arrived. So the fake information simply change the arrival to leaving. And in this image, if you didn't go to Berlin or Milan, probably it's hard to tell whether this train station is Milan or Berlin. So a fake caption will simply replace the place name from Berlin to Milan to fool people. Sorry, from Milan to Berlin. Okay, so my point is that for a lot of the fake news documents, the fake information is not just like the whole document level is fake, but rather we should look into knowledge graph and then figure out which subgraph is fake and then fix that. So compared to the previous work, we are looking at the multi-modal consistency checking, and we are also looking at the knowledge element level detection. And we believe this kind of missing information detection can make the results much more explainable, because you not only show people why this is fake, but also show how that fake information was created. So the idea is to apply what we have already mentioned about the multimedia information ingestion to construct a multimedia knowledge graph. And then we're going to train a model binary classifier to apply that to every triplet, and then classify every triplet as a true or false. For example, here all of these triplets are false because they don't have the supporting information from another data modality or from other parts of the document. So for example, here, the caption is fake because this place was not shooting onto the crowd. So what we need to do is to construct multimedia knowledge graph, and then we do cross-media coreference resolution to link this shooting event with the shooting event that appeared in the caption and in body text. And then we also do object coreference resolution to ground these bounding boxes into the entities we extracted from the body text and the caption. And then within each data modality, we have a knowledge graph. So we can then look into every triplet to see whether that's consistent with other neighborhood. And then across data modalities, we can also see whether the triplet that are coreferential across data modalities, whether they are consistent or not. If the image said the police was not shooting at the crowd, but the body text provide different information, then that's inconsistency. So the major challenge for this task is that we don't have any training data, right? Because human generated training data usually will be removed immediately after they appear on the web. So our idea is that, again, use graph generation to generate fake documents automatically as training data. So one big disclaimer here is that we are not going to share our generator. Well, we'll share our detector for sure. So the idea is that we are going to take any authentic article as input and then construct a knowledge graph and then do some manipulation on the graph. For example, we are going to switch some entities and we'll add relations or events, and then we will use graph to text generation to generate the fake documents for training. But we need to follow some certain criteria, otherwise the manipulated fake documents are very easy to detect, right? So that's not what we want. For example, if we look at this document, if we replace the bicycle with the truck, then any human or system will be able to detect this as fake information because clearly the image shows bicycle, right? So we don't want to touch any entities that are already grounded in the image. So we apply a cross-media grounding system to remove those entities from our candidate list. And then for other entities such as Zambia, which is not grounded in the image, we are going to replace Zambia with another country name called Fiji, which is semantically similar to Zambia. And then we use graph to text generation to generate a new article. For captions, we further use the AMR graph because AMR covers more relation types than the knowledge graph. So we apply the similar idea. We convert the sentence, real sentence into AMR graph, and then replace some certain relations and nodes in the AMR graph with the new ones, and then generate a fake caption automatically. And then we use this for training. So to check the difficulty of detecting information from this kind of automatically synthesized data, we did a tuning test. We showed a pair of real news and fake news to human and ask them to figure out which one is fake or which one is real. So they only could, they were only able to find 42% of the real documents. They can only detect 42%. So that means our automatic generated fake documents include some facts that are very difficult to detect even by human. We compared our methods with several SOTA methods that did not use graph structures. So Grover is based on sequence to sequence. Dedan is based on cross-media and also only looking at the sequence on the text side. So we can see that our model outperformed them on data that's generated by Grover, and this data is generated by our graph to text generation method. Our knowledge element level performance is also quite decent, much better than baselines. So here, just showing you another successful example. This facility was not grounded in the body text, so it's a fake. The body text is a fake, and our system is not just able to find this as misinformation, but also tell us the triplet British Twin Towers is a fake information. Okay, so all of these systems are shared as Dockers and open source code, and we also have some demos online. You can play with them. Thank you.
Hello, everyone. So I'm Bang Liu from University of Montreal. So next, I will introduce how graph representations and graph neural networks can be applied to text clustering and matching. So nowadays we are expressing information explosion. So we have many different information by news media, and it's not an easy task for us to quickly retrieve what we actually want from so many different information. So traditional search engines or feed news streams, they will provide us a list of documents based on our queries. For example, if you input Trump-Hillary United States presidential selection, you will have like different news articles reporting these new events from different news media. And such results have multiple disadvantages. So first is like the results are immersed document lists, and they provide us extremely fine-grained information. So they provide us different articles, and it costs a lot of time to read these articles. And they will contain redundant, useless information because different articles from different media, they will convey like multiple similar information. And also they are unstructured because different articles, they only have an order of relevance. They didn't have a relationship between them to show us like how different articles are connected to each other. So we propose the story forest system, which aims to reduce the information redundancy and help users to track relevant events around the world. So basically we have different nodes and organized as a tree. So each node contains articles reporting the same events, and the correlated events are connected and as the branches in a tree, so that they show that different events are close, like related to each other. And each tree of events, we call it a story. So for details, you can retrieve to the paper published in like the TKDD 2020. And here shows the overall structure of the story forest system. So we want to go into details here, but basically it contains 4 components. The first part is preprocessing the incoming stream of documents. And then we perform an even X clustering algorithm to divide a stream of documents into different events, where each event is a cluster of documents reporting the same incidential event in the world. So basically it's a 2-layer graph-based clustering. So we first construct a keyword graph from the keywords of all the documents. So we perform community detection over this keyword graph to divide it into subgraphs. Then we assign documents to its most similar keyword graph here to perform the first layer clustering. And then we classify each pair of documents in one document cluster to establish the document pair edge, where each edge indicates like the 2 documents are talking about the same event. In this way, we have a doc graph for each cluster. And then we apply community detection again to divide this document graph into multiple subgraphs. Then the final subgraph from the second layer clustering is our events. And then we have a growing story forest module to connect different incoming event node to existing story tree, or construct a new tree based on its content here. And such systems are actually applied in real-world mobile applications, which is the Tencent QQ browser hot topic list product. So basically, the product provides a list of hot events for every hour of every day. Then, for example, here we show the Hawking public his PhD thesis. Then if you click on this hot topic, if we have a list of documents reporting this hot event from different media. And actually, the core task in what we have described the system is like how to judge the relationship between two long articles. And actually, this is a text matching task. And actually, there are numerous text matching tasks based on the length of the input source and output target. For example, text pair matching or ad hoc retrieval, your input is short query and output is long document. Or like document classification, your input is long document and output are like short labels. So when we perform long document matching, so basically we want to identify the relationship between two news articles so that if two news are talking about the same event or the related events, we can know the relation. If they are not related to each other, we can like divide them into different stories. In this way, we can help to track the information among different articles and remove the redundancy. So existing algorithms for text matching are mostly developed for short text pairs, for example, sentence matching. But for long document matching, they are not suitable because the lengths are too long. And if you shuffle the sequence order in a document, the meaning almost doesn't change, but it will have a big influence on the final result of the text matching algorithms. So in this way, we perform a divide and conquer algorithm. So basically our strategy is first we divide each document into multiple short paths. Then we align the different short paths in two documents. And finally, we can perform distributed matching over each local short path matching. In this way, we actually transform the long document matching problem into a multiple short text matching. Then we aggregate the short text matching results to get the final matching result. In this way, we can more easily encode the information of long documents. We can handle the flexible order of the sentences or paragraphs, and we can reduce the time complexity by this divide and conquer strategy because we can perform distributed matching here. So here shows an example. So basically for this long document matching algorithm, we propose a graph representation called concept interaction graph. So let's say with this toy document example, so we have 6 sentences here. And the first step is we will extract keywords from this document. So basically the keywords are the red words. And then we can construct concept nodes. Here a concept means a cluster of keywords which are correlated to each other. Basically, we use the same algorithm for the keyword community action. Then each community of keywords are a concept node in this document. And then we can divide the sentences in a document into multiple parts by calculating the similarity between each sentence and each concept nodes. Then we select the one with the maximum similarity to assign it. So if we have like a pair of documents, we can just like for each concept node, we can have 2 lists of sentences, one list from document A and one list from document B. So then we can construct the urges. Basically, we concatenate the sentences for each node. Then we calculate the TF-additive similarity to construct a weighted urge. So if the weight is below a threshold, we can remove the urge. So in this way, we can say that we actually decompose the content of 1 or 2 documents into multiple paths, and we show the connection strength by the similarity. So here is the long document matching algorithm, which is called the graph decomposition for document matching. So we first construct the concept interaction graph from a pair of documents, document A and document B. Then for each node, we have like 2 lists of sentences from A and B. We can perform a short text matching by different algorithms. For example, we can calculate sentence similarities, or we can apply a Siamese neural network to encode the 2 pieces of sentences first from 2 documents and compare the result. Basically, we can get a local matching vector for each node. Then we go to the part C we have a graph structure, and for each node, it actually is a subpart of the two documents. We have a matching feature vector. Then we can propagate it into multi-layer graph convolutional network, and then aggregate all the transformed local matching vector into a global matching result. And finally, we perform classification by a softmax layer. Then we get the final classification result. So our experiment shows that actually the graph representation can greatly improve the performance. So compare this method 9 and method 11. The only difference is like in the second algorithm, we actually decompose it by graph representation, and we didn't use convolutional neural network, graph convolutional network, but it already improves the performance. And then if you compare two algorithms, one with the GCN propagation and another one without that, you will see that the accuracy and F1 score further improved a lot. So from this experiment, we can say that both the graph decomposition and the graph convolution helps a lot to improve the performance of long-document matching. So next, we will introduce how graph representation and graph neural networks can be applied for text mining and classification. For mining, we're talking about like extract different phrases from queries or documents. And for classification, we are talking about assign a label for document or query. So basically, it can be like both fine-grained tags or coarse-grained as labels. This can help us to improve the understanding of both short queries and long documents, and improve the performance of search engines and recommender systems. So, for example, in this case, if a user is searching something in a browser, so what is the user interested in? So we want to infer the user's interests. So if the user input a query, trace-based representation speech, if a search engine will extract the keywords resume, and then it recommend other articles about resume, this will may cause a problem of inaccurate recommendation, because this user may be not interested in the keyword, basically the resume, because he or she is not a fan of resume. And the search engine or recommender system may also recommend like other articles about resume representation speech. This will cause the problem of monotonous recommendation. Because the user already read articles about resume representation speech, he or she doesn't need to read another article with similar information here. So a good recommender system may recommend articles about Brexit negotiation because it matches the user interest. So to achieve such kind of a performance, we need two key parts. First, we need to be able to extract such kind of suitable granularities interest. For example, we need to extract the Brexit negotiation as a potential interest. And the second is we need to identify the relationship between user interests. We must know that the event trace-based representation speech is actually belonging to the topic Brexit negotiation. So how we can do that? So first, let's talk about what are users' interests. The first is like users are interested in different events around the world. For example, trace-based representation speech, or Apple launched new iPhones here. So we can define event as a real-world incident that involves specific persons, organizations, or entities with a certain time, location, or occurrence. Another type of interest are concepts. So basically, a concept is a collection of things that share some common attributes. For example, Honda Civic and the Hyundai Electron are all fuel-efficient cars or economic cars. The Iron Man and Captain America are all Marvel heroes or Avengers. So these are all concepts. So we propose to the giant system to create an attention ontology. So basically here, this ontology contains heterogeneous nodes and urges. So you have like different categories or concept node, entity node, type or events, and you have the either relationship or involved relationship or correlated relationship. So basically the main problem here is like how we can extract different phrases, basically the concept nodes and event nodes, so to be added into this giant attention ontology and identify the correlations here. So this is the whole architecture of the giant system. So it shows like how we actually construct such an ontology from the user's browsing data. So basically, users will input queries, and these queries are associated to top-clicked documents. So in this way, queries and documents, they form the bi-party graph by the click action. And the first, we will cluster this click graph into multiple query clusters, while each cluster contains several queries and documents. They are very similar. And then in the second part, for each query document cluster, we extract a phrase, maybe like a concept phrase or event phrase, or we cannot extract anyone based on the input. So if we can actually extract an output phrase, we can consider it as a new node to this attention ontology and try to identify the relationship by associating it with a parent node in this ontology. And based on it, we can tag the user's interests, and we can tag content of document or query, or help to construct the story tree. And then, based on the tagging of both users and documents or queries, we can merge the content so that it can help to improve the recommendation performance. For example, if a user is interested in fuel-efficient cars, and we know that a document is talking about the fuel-efficient cars, we can help to improve the performance of the recommendation. So the key research problem here is like how we can perform heterogeneous phrase mining. So basically, we have inputs. Input contains multiple queries or multiple titles of the documents, and we want to extract a phrase. So, for example, in this case, the output phrase is a concept. We have one query and 3 titles, and the red, the Hayao Miyazaki animated film is the concept we want to extract. So if you analyze the inputs, we will observe multiple characters. For example, basically the phrase in the query or titles, it will show some patterns based on the dependency structure, and it will show up multiple times because if you are interested in this Miyazaki animated film, you will mention it in the query, and the corresponding documents will also mention it in the title of the content. And also the named entity or part of speech text are important features to decide whether a word may be a part of the output phrase. And also most of the time, the words will be continuous in the query title. And the syntactic dependency between different words in the concept node will be similar, even though they show up and may have different forms in the query or titles. So we proposed the query title interaction graph to encode all these features to make them more obvious and to help us to extract different phrases, both the concepts or the event phrases, very efficiently in a unified manner. So basically here, first we append a virtual start of sentence and end of sentence node for each query and document title. And then in this graph, each node is a unique word among all the queries and titles. And then if two nodes are basically 2 words are adjacent to each other in any of the query or title, we can append a sequential urge, SQ, between them. And then if 2 nodes are not adjacent to each other in any place, but they have a syntactic dependency, we will add such a syntactic urge between them. And for each urge, we have both the forward direction and the inverse relation, so that each urge is bidirectional, but the forward and backward are different relations. So in this case, we can say that the patterns can be captured by the graph structure, and the node feature can encode how many times each word show up, and what is the named entity or part of speech tag. And the sequential urge indicates the continuous feature, because if you have like a sequential urge between 2 nodes, you know they are like close to each other in one of the query title. And the syntactic dependency can be captured by the syntactic edges. So based on such representation, we can extract the phrase. So here is how we do that. First, we will perform a node classification by relational graph convolutional network. So basically, it's a binary classification. And then we remove all the non-sequential edge, and we remove the backward edge of the sequential. We only keep the forward part, the direction edge. And for others nodes, we didn't clear what are the words exactly. And next, we need to find a sequence to connect all the positive nodes to form, to connect them into an output phrase. Basically, this is the problem of asymmetric traveling salesman problem. So what we want is we want to find a path between the start of sentence and end of sentence. And we want to connect all the positive nodes by a path, which is with the minimum length. So this is exactly the asymmetric traveling salesman problem and can be solved by fixing algorithms. So we have introduced how we can extract text or different concepts or even text from queries and documents. The next is how we can perform document classification to associate top nodes to the or categories to different documents. So in this paper, they perform transductive text classification with text GCN. So basically, they construct a graph where the nodes are words and documents in a corpus, and the edges are the co-occurrence edge or TF-IDF edge between each word and document. And then they model the graph with a graph convolutional network and perform node classification. So in this way, we can get the label for the document node. And we can say that the performance of text GCN is much better than other baselines without graph convolution or graph structure. And the embedding learned by this graph neural network are much better than others if you look into the TSNE visualization. And in this paper, they proposed utilize the text ing to further improve the performance of document classification with graph-based algorithm. So basically, in the previous algorithm, they are performing transductive classification because they form a big graph for all the documents and then perform node classification. In this way, you need to know the text document in advance. But in this paper, they construct each document as an individual graph, and text level word instructions can be learned in it. So the nodes are words in the document, and the edges are co-occurrence edges. And they model the graph with a gated graph neural network, and then gated graph neural network. And so this can help to generalize to new words that are absent in training, because new words can learn feature from its neighboring words. So in this way, basically, we first construct a document graph, then we propagate it into gated graph neural networks, and we have a readout function to aggregate the embedding of words into the document embedding, and then we perform classification. So here shows that the performance of text ing is better than text GCN, and it's also if the training data is much less, then the advantage of text ing is even much more obvious here. So basically, this shows the similar conclusion with what we have shown in the long document matching, because the decompose long document by graph representation will be very helpful than just consider it as a non-structured representation. And actually, we applied this system, the giant system, to the fifth news recommendation in the QQ browser, mobile QQ, and so on. So, and basically, for example, this shows an example. If you have a document with this title, you can tag the concept tag the low fuel consumption task to this document, even though this concept phrase never show up in the title or the content. In this way, it helps the understanding of the long document and improves the performance of recommendation. So to summarize, the graph neural networks enables the encoding of multi-scale information of text and the heterogeneous information of text, because it can encode like the multi-levels, the word information, sentences, or documents, and you can encode the different edges, such as the co-occurrence or syntactic edges and so on. Thank you.
Next, I will introduce the applications of deep learning on graphs techniques in natural language generation and machine translation. We will first talk about natural question generation. So the task of natural question generation aims to generate natural language questions from a passage and an answer. Ideally, the generated questions are supposed to be relevant to the given passage and answer. The QG task has many useful applications, such as providing training data for QA systems. This SIGIR2021 paper proposed an RL-based graph-to-sequence model for the QG task. As we can see from this diagram, the model consists of a Geon-based graph-to-sequence generator and a hybrid evaluator combining both cross-entropy-based and RL-based objective functions. In order to better capture the rich structure information hidden in the passage text, they constructed a passage graph which contains each word in the passage as a node and apply a GNN to encode the graph. As for graph construction, the authors explored two different strategies. One is syntax-based static passage graph construction, where a dependency graph was constructed. And the other is semantics-aware dynamic graph construction, where node embedding-based similarity metric learning and a KN style specification were applied. Because the constructed graph is a directed graph, the authors applied the bi-directional GNNs to encode the graph. Specifically, they introduced the bi-fuse GNN as the graph encoder. The experimental results showed that static graph construction performs slightly better than dynamic graph construction. And bi-directional GNNs performs better than unidirectional GNN, and the graph-to-sequence performs better than sequence-to-sequence. The next application we will talk about is natural question generation from KG. This task aims to generate relevant questions from a KG subgraph and a target answer set. The key difference with question generation from text is that its knowledge source is a KG subgraph instead of free-form text. Because the input of this task is a KG subgraph plus answer set, it is quite straightforward to apply a graph-to-sequence framework to this problem. As for graph construction, the authors extracted a KG subgraph surrounding a topic entity. And as for graph representation learning, the authors explored two strategies. One strategy is to first convert the KG subgraph to a homogeneous graph via Lavi graph construction, and then apply the bi-directional GNNs to encode the graph. The other strategy is to apply multi-relational GNNs to encode the KG subgraph. The experimental results showed that Lavi graph conversion plus a homogeneous GNNs performs comparable with multi-relational GNNs. And its ablation study showed that the bi-directional GNNs performs better than unidirectional GNNs. Now let's talk about the summarization application. So the task of summarization takes as input a document, a dialogue, code, or multiple ones, and outputs a succinct sentence or paragraph, which summarizes the key idea of the input data. This SIGIR2021 paper also applied the Geon-based graph-to-sequence framework for the code summarization task, which aims to generate a natural language sentence to summarize the code. As for graph construction, they propose to combine the static CPG graph and the attention-based dynamic graph. As for dynamic graph, they apply the structure-aware similarity metric learning, which utilize the edge information of the static graph. They also combine the intrinsic static graph and the learned implicit graph for better performance. As for graph representation learning, because the constructed graph is a multi-relational graph, they apply the multi-relational GN to encode the graph. Specifically, they proposed a hybrid GN which runs message parsing on both static and dynamic graphs. And the experimental results showed that combining static with the dynamic graphs performs better than only using the static graph or the dynamic graph. Now let's move to the machine translation application. The machine translation task aims to convert the source language text to a text in a target language. This Nlp 17 paper proposed a GN-based model for better capturing the syntactic information of text for machine translation. As for graph construction, a dependency graph was constructed to capture the syntactic information of text. As for graph representation learning, a multi-relational GN was applied to encode the graph. And the experimental results showed that syntactic GCN is quite helpful at capturing the syntactic information for better machine translation performance. And this ACL20 paper focused on the multi-modal machine translation task, which in addition leverages the visual information to guide the machine translation. The authors constructed a multi-modal graph where all the vision nodes are fully connected, all the texture nodes are fully connected, and the edges between the visual nodes and the texture nodes were established based on certain domain knowledge. As for graph representation learning, they applied a heterogeneous GNN which employs graph attention for intermodal fusion. And the experimental results showed that their model performs better than the previous models.
Now we are ready to go in our hands-on demonstration part. So we will first introduce our graph for NLP library. This is the first library for easy use of the graph journals for NLP. This is the overall architecture for our graph NLP library. As you can see here, that we have 4 different parts. So first, we will, if in terms of hardware, currently we are support the CPU and GPU, and for the backend, currently we are only support for the PyTorch, but we are ready to support for TensorFlow later. And we are building on the several runtime library, like a deep graph learning library and Hugging Face, to leverage the pre-trained BERT embedding. For our graph for NLP part, we have 4 layers. The first layer is graph and data layer. The second layer is our module layer. We have a graph construction, we have a graph units, we have a prediction, loss, and evaluation part. And beyond that, we also have a high-level model layer that we provide Gradual sequence, Gradual tree. We'll also provide Gradual graph model once we have been choosing a general framework for that. And on top of that is variance of the different NLP tasks. Currently, we have been provided more than 12 different NLP tasks supported by our library. And you also feel free to develop a new NLP task built on this building block that we have been providing here. And here is our basic graph for NLP library. You can see that so we have modules, we have models, we have applications, we have the data and graph data component. So here is our data flow for our graph NLP. With the raw data, we can fix the raw data to a graph construction module. Question module will generate the raw data into our graph NLP graph data module. And once we have this data, we will feed that to the graph embedding method, and then we can generate a bunch of the node embedding, and then we can feed that to the downstream to the prediction module. And based on the result, you can do the evaluation or do the loss function. This is a basic computing flow for our graph NLP. So there are 2 different scenarios. The first scenario is that this is probably the most often case is that we have a text sequence, And then you can call our Statical Graph Construction module to construct a graph for you. In the graph data, we will build a two part. One is a topological construction, one is an embedding construction. And after that, we will feed to the dynamic graph construction. This is optional if you already have a static graph construction. But the static graph, if we don't have a static function, then you can, in this part, you can call our dynamic graph construction module. And then we can feed that to graph neural network method to generate node level or graph level embedding. And then we can do either node qualification, link prediction, or graph prediction, or we can do a sequence entry or graph decoder. So here is a bunch of the performance using our built-in NLP task. We're showing that with our library, we can achieve similar performance that is reported in the different literature. And I have been here showing different tasks, and we have been using different graph model, graph construction module, and evaluation metric. And you feel free to report your own. Okay, next will be our live demo, and that I will give my floor to Yuchen to further illustrate two different cases.
Now it's live demo time. In this demo session, we will together use the Graph4NLP library to build Geon-based models for NLP applications. The first demo will be building a text classification application. Please clone the Graph4NLP demo repository on GitHub and follow the get started instructions in README. So here's our Graph4NLP demo repository on GitHub. In order to run the demo code, you will need to first install the Graph4NLP library. Please follow the environment setup instructions here to install the library. And also, please feel free to refer to the Graph4NLP repository page for more details on how to use the library. So once you install the Graph4NLP library, you can start the Jupyter notebook and run the demo. So here you will need to change the XYZ to the SIGIR2021 folder. In this text classification demo, we will use the Graph4NLP library to build a Geon-based text classification model. The model consists of a graph construction module, and a graph embedding module, and a prediction module. We will use the built-in module APIs to build the model and evaluate it on the TREC dataset. So you can directly run this demo if you already installed the Graph4NLP library. So now let's get back to the slides and to see the various components of the demo code. So this piece of code shows the overall architecture of our model, which contains 3 steps. The first step is to build the graph topology. And the second step is to run a Geon encoder. And the third step is to run a graph classifier. So here we call the graph construction API to create a graph topology builder. There are various building options provided by the library, including like dependency graphs, constitutive graphs, and IE graphs. And the library also supports customized graph construction modules. And here we call the Geon API to create a Geon instance. And also there are various building options provided by the library. For example, the GCN, the GAT, and the GGN models. And also one can like create customized Geon modules using the library API. And here we call the prediction API. And again, there are various building options provided by the library. And one can also customize their own prediction module. And here's the dataset API, which can also be customized. Now let's talk about the second demo, which is to build a semantic parsing application. Let's quickly go to the Jupyter Notebook page. So in this semantic parsing demo, we will use the Graph4NLP library to build a Geon-based semantic parsing model. So the model consists of a graph construction module, a graph embedding module, and the prediction module. So for this demo, we will use the built-in graph-to-sequence model APIs to build the model and evaluate it on the jobs dataset. So the graph-to-sequence model APIs is higher-level APIs, which we can directly call to create a graph-to-sequence model instance. So let's go back to the slides. So for this demo, we can directly call the graph-to-sequence model API provided by the library to build the graph-to-sequence model. Here we call jobs dataset API. Jobs is the dataset we are using in this semantic parsing application. And again, there's various building options in this dataset API. For example, one can specify which type of statical graph construction we want to use because statical graph construction is conducted during pre-processing. So we want to specify it in this dataset API. Yeah, so here are two applications we can build using the Graph4NLP library. Please feel free to check out more application examples in the Graph4NLP repository on GitHub.
Now we are able to talk about the future direction and conclude this tutorial. So as you can see here that in the last few years, the topic of the graph neural nets and natural language processing have been attracted a lot of interest. So we believe that the graph neural nets of an NLP topic will become a trending topic in the future. So there are a few of the very challenging topics or problems that we should address to further advance this area. The first thing we want to talk about is graph construction technique for NLP. So as you can see here, that the dynamic graph construction have been largely unexplored. So then the natural question will be asked, how can we effectively combine the advantage of the static graph and dynamic graph? And so far, we only see when we using dynamic graph, most of the time we only can able to generate for a homogeneous graph. But how about the marginal graph? How about the heterogeneous graph? So is there any way we can construct that effectively, just like a static graph that we can able to generate all different kind of graphs? And also we want to point out that the dynamic graph construction itself is also expensive. So as shown in the previous, discussed in the previous part, so the dynamic graph often involving pairwise similarity computation between the graph node. That means that it will have a quadratic complexity in terms of the number of nodes. So how to scale up this part of the computation is also a very important topic. At the meantime, we are also needed to develop a more new method to try to scale up the graph neural net computation to the large graph. Especially most of the existing multi-directional and heterogeneous graph neural nets that all have this scalability issue. But in NLP domain, such as large graph, it's very common that we often have a very large graph. So this is also very important. Another important topic is that the graph neurons and the transformer are both very successful technique in being well known in the NLP domain. So how can we effectively combine the advantage of the graph neurons and transformer? Although the transformer is a special type of the graph neural nets, so they still have a very different architecture try to learn the representation. And currently we have seen people using graph transformer try to unify the both two techniques. However, is a graph transformer is the best way to leverage the advantage of the both work. So this is also questionable. So this is will be a very important research area. So we have been seeing a lot of the pre-training technique for the NLP today, especially leverage on the transformer architecture. However, the graph neural is also a very flexible architecture, especially that it can take advantage of existing graph structure information. In that case, how can we do pre-training for graph neural nets for NLP? It's a very interesting direction. Especially, for example, in the information retrieval and search, people have been trying to also using graph feature for all kinds of these downstream tasks. So in that case, the pre-training technique will become very important. We have been also see that, so often we see that the input could be a graph structure information, and the output could be a graph as well. Like in the information instruction, it's naturally we will transform the, for example, as introduced by the Professor G, that we can leverage AMR graph and then translate to the IE graph. So in that case, so how can we develop an effective graph model for solving this kind of a graph transformation problem in NLP? I think it's a general, it's a very general learning challenging. And also we can consider how to join the text and causal reasoning in NLP, so that although that the text reasoning, especially in the multi-modal reasoning, have been explored before, but how to do the joint text and causal reasoning is less explored. And we can also consider how to incorporate the source and context into knowledge graph construction and then verification. So this is also a very important topic for the information instruction. And finally, I would like to conclude this tutorial. So deep learning graph for NLP is a fast growing area today. As you can see that, so the graph can naturally encode many complex information. Therefore, that it can really bridge a gap, so that we can combine the empirical domain knowledge and the power of the deep learning. For a given NLP task, it's have two important questions to ask. The first question is, how can we convert a text sequence into a base graph? It will be a direct graph, multi-directional graph, or Heterogeneous graph. And once you have a graph at hand, then how do we determine the proper graph or general learning technique in order to make full use of the graph information we have been constructed? So here we are also present our graph for NLP library, which is M2, make easy use of the graph neural nets for NLP. We have been provided the code. We have been provided our survey paper. This survey paper is a very long survey paper. We have about 127 pages. We have been surveyed more than 500 literature in the top AI machine learning and NLP conference in the past 5 years. In order to give a very comprehensive survey on the graph neural nets for NLP. We also provide a demo code. We also have a GitHub literature list for people to check out, so that you can get more familiar with this area. And that's all for our graph for NLP tutorial. Thank you so much for attending our tutorial, and we are looking forward to have a QA session and also have an online demo session with you in the SIGIR IR in July. Thank you. Bye-bye.